Welcome back to a new episode of Passion for Technology, the podcast from EPD Electronic. Great to have you with us.
Welcome to the Passion for Technology podcast. In this episode, we'll be taking a closer look into technology trends in terms of manufacturing wide-bandgap semiconductors based on silicon carbide and gallium nitride. The current market size for wide-bandgap semiconductors is estimated at around $600 million globally. That's a fraction of the market for regular silicon-based semiconductors. Manufacturer estimates paint a promising picture for the near future. The market for wide-bandgap semiconductors is bound to more than triple in size until 2025. We'll be diving deep on the challenges that need to be tackled in manufacturing for an increased level of industrial maturity. I'm your host, Mustafa Isik. I'm happy to welcome our guests, Filippo Di Giovanni, Strategic Marketing, Innovation, and Key Programs Manager at ST Microelectronics. Hi, Filippo.
Hello.
And Dr. Kevin Speer, Senior Manager, Silicon Carbide Power Solutions at Microchip. Welcome to the show, Kevin.
Hi, Mustafa. Thanks for having me.
Both of you are working on the manufacturing side of the business. Both of you are predestined to provide first-hand insights into what these new semiconductor materials mean for manufacturers and the trends in series production. Kevin, what do you consider to be the biggest challenges in working with silicon carbide and GaN in production?
Yeah, so I think let's just go ahead and get something obvious out of the way here right up front. Engineers and scientists are inherently a skeptical group of people. We're taught to identify the worst case conditions and base our objectives around these. And so it goes with silicon carbide and GaN. Power electronics engineers, with their healthy doses of skepticism, are searching for the worst cases, and the moment they get a hit of smoke, there must surely be fire. The reality is that silicon carbide is progressing even more quickly than silicon did because of the lessons we learned with silicon. And in particular, silicon carbide has reached a very high level of maturity in production. But at Microchip, we have our own production line. And when we combine that with our foundry partner and quite common yields, our capacity is virtually infinite. So again, with respect to silicon carbide, I don't see production challenges that we didn't encounter and overcome long ago with silicon. And speaking of silicon and the maturity level of silicon carbide, what we're all doing in the industry today is looking at ways to take what is already a robust, disruptive semiconductor material and identify ways to reduce cost. So this could be through techniques that have become pedestrian in the silicon world, such as wafer thinning. In short, incoming material quality and capacity are both steadily improving, and process technology and device yields are fast approaching what we've long been accustomed to for silicon.
So I have to say that the main challenge that we had to deal with was the supply of substrate in the beginning. This was the major problem that we had to solve. But today, this is completely solved for two reasons. Number one, we signed a strategic supply contract with some partners in order to get enough material, enough substrates for our short and medium-term needs. In the meantime, as we want to implement a vertical integration, we acquired a Swedish company, Norstel, which has been incorporated in ST. So we will be free to produce our own substrates in the near future. So this is the main problem that has been completely solved. The other problem related to production is the fact that inherently the silicon carbide has some defects that cannot be removed so easily. So implemented automatic testing methods in production, especially when we test wafers, in order to screen dies that could possibly have problems. So this was another major step forward. So as Kevin said, today we don't see any major problems. And in fact, more and more customers starting devoting interest and attention to the silicon carbide products. Even the most skeptical customers that were hesitant before using silicon carbide are now appreciating the big advantages of this material.
Focusing a little more on this, how would you describe the level of maturity of modules utilizing SiC and GaN? Kevin.
This is another excellent benchmarking question, Mustafa, and it really depends on the power levels under discussion. The evolution of multi-chip power module packaging for both silicon carbide and gallium nitride is going just as it did with silicon MOSFETs and IGBTs. So what I mean by that is as the die ratings, specifically that could be blocking voltage and current or RDS on in the case of MOSFETs, as the die ratings increase, so does the serviceable market for these components. As the serviceable market grows, the demand for innovations and packaging become more urgent. So for the wide bandgap community as a whole, I think we can be doing more to optimize the packages, both from a thermal and electrical point of view. This is really the only way end users can fully realize the performance benefits made possible by wide bandgap. For example, at Microchip, we offer a phase lag power package for silicon carbide with an industry best 2.9 nanohenries of parasitic inductance. With this very low parasitic inductance insertion into the power loop, customers can finally extract the low switching losses and the efficiency of silicon carbide without having the problems of EMI, voltage overshoots, and things of this nature. So as a community, we are all marching toward that same end goal. We are making progress there, but there's still quite a bit more to do.
What would a behind the scenes look into your laboratories reveal? Filippo, what aspects are you focusing on in terms of manufacturing with wide bandgap semiconductors?
Okay, let's start from silicon carbide because we started working on silicon carbide more than 20 years ago. And we had a strong collaboration with CNR, which is the National Research Institute in Italy. And their laboratories are physically located inside our premises. So we started playing on 3-inch, then 4-inch, and so on. So we basically started understanding the potential benefits of this material many, many years ago. So we have a lot of IPs and patents on this material. So, we worked a lot trying to understand the failure mechanisms of this material because, you cannot think of starting mass production with a brand new technology if you do not master the technology itself. So we devoted a great deal of effort and time to understand the physics of this new material. And then we implemented efficient methods to screen the defects that are present in the substrate and can propagate into the material during the fabrication process. It cost us a lot of time, but in the end, it was worthwhile. So this is the reason why today ST is number one in the production of silicon carbide MOSFETs worldwide.
Mustafa, a behind the scenes look into our laboratories usually requires an NDA and a security badge. And of course, we can't get those things in place in time for this podcast. But what I can tell you is that Microchip, after acquiring Microsemi, brought in the high rail legacy of Microsemi. And we continue to hold true to our promise of differentiation along the ruggedness and reliability aspects of our silicon carbide power products. This will continue to be a prevailing priority for Microchip. At the same time, we're looking at ways to differentiate across our entire capability suite, whether that's silicon carbide die design, processing techniques, advanced power packaging, like I mentioned before, digital programmable gate drivers, could be microcontrollers, and of course, there's more. The priority of our products at the end of the day is reliability and ruggedness. The priority of our research labs then is enabling customers to use those products easily and effectively.
Increased demand for SiC and GaN requires for continually increasing production volumes. Kevin, when do you think will it be possible to produce quantities comparable to the output and quality of silicon wafers?
Lots of healthy skepticism around wide bandgap and comparisons to silicon. But let's remember that silicon has been around for much longer, and a great deal of the global silicon power device capacity comes from pure play foundries. So to that point, we have seen increasing pure play foundry activity, largely kickstarted by XFAB in Texas, who happens to be Microchip's foundry partner. And then just these past 2 to 3 years across the globe, there are more and more pure play foundries emerging for silicon carbide and also GaN. And I believe this is going to do a lot to ballast the existing internal capacities of IDMs like Microchip.
Filippo, what's the current state of wafer sizes for wide bandgap materials? Do you think that it will be possible to have SiC and GaN wafers as large as silicon wafers?
Good question. Let's start from gallium nitride. Today, most of suppliers are producing at 6-inch, whereas ST decided to start production at 8-inch directly, skipping 6-inch. And this is per se a big improvement. Of course, we still rely on substrate suppliers to get improved quality substrates and eventually possible wafer enlargement. For silicon carbide, the situation is a little bit different in that basically 100% of manufacturers are using 6-inch wafers or even 4-inch. Thanks to the fact that we acquired Norstel, so we have full control of the substrate production in-house, we have already started actions in order to introduce 8-inch wafers for silicon carbide. I am pretty confident that in 3 years' time from now, we will be able to produce also internally 8-inch substrate. So it took much longer to silicon to switch over larger wafers. But I think with the new material, this process will be much, much, much faster.
How are power semiconductor designs changing as a result of using SiC and GaN, Kevin?
So wide-bandgap semiconductors open possibilities to designers that could have never been possible with silicon. So the very performance benefits offered by silicon carbide and gallium nitride are, in fact, the root cause of many design challenges. For example, we can make converters smaller and lighter due to faster switching speeds, but with improper design, those faster switching speeds may also lead to high overshoot voltages, EMI noncompliance, or other issues. So we will absolutely realize the disruptive benefits made possible by silicon carbide, but we have to really take a step back and view the system holistically and look to offer our customers total system solutions to help them cross the chasm with silicon carbide and adopt it effectively.
You mentioned EMI overshoots. So, Kevin, do you think that testing procedures and standards also need to be modified?
For sure. As we push design envelopes, of course, we have to ensure that the standards we place on those components follow along. Microchip is an active participant on the JEDEC 70.2 committee that creates these standards for silicon carbide and gallium nitride. And we feel the group has done an excellent job of making sure that the community as a whole is putting out quality products into the market, just like we've come to expect of silicon.
At ST, of course, we are in the same group working with partners and other competitors in order to define new standards, new qualification procedures, because the material is different. So must be the testing procedure and the qualification plans. But let me remark that we started producing silicon carbide for the automotive industry from the very beginning. So we knew the constraints and the criteria of the automotive industry. So our technology was extensively debugged in this harsh environment. And after doing that, of course, we were ready to offer the same level of quality to the industrial customers. Because normally what happens is that you do the opposite. When you deal with a new technology, you develop it for the consumer or industrial market, and then you ruggedize it for the automotive industry. We took the opposite step, and this was very beneficial because every industry can have good quality silicon carbide products. In terms of testing, yes, the procedures are different and more stringent. For silicon carbide, for instance, it is absolutely imperative to screen defects that otherwise would be incorporated into the final products. So we have very advanced techniques in order to remove dyes that could be potential harmful.
Looking at the surrounding components, so what effect does the use of SiC and GaN semiconductors have on neighboring components, connection and housing technologies, for instance, Filippo?
Well, for the designer, in the end, it's all about trade-off. We, as a semiconductor supplier, we have developed very advanced products that can bring really a lot of advantages. So we are offering so much margin to the designers that their job can be made easier. From the other hand, we know that in a PCB, there are also passive components like inductors and capacitors. So it's up also to the suppliers of these products to speed up the improvement of these products. What is important is that the improvement margins we are giving with the new materials is so ample, is so huge, that in the end, the designers will be much better off in optimizing a given circuit, PCB or something like that.
And if I can, Mustafa, I'd like to ride the coattails of my colleague Filippo here. I think the effect that this is having on the suppliers of neighboring components is that this is creating very busy work days for them. Indeed, with silicon carbide, we can operate at temperatures which were impossible for silicon, so much higher, in fact, that the semiconductors are no longer the limiting component. So, therefore, this creates a challenge for the manufacturers of these surrounding components to increase their safe operating temperature range as well. Having said that, kind of like Filippo said, suppliers of silicon carbide components are not free of responsibility either. Packaging technology must also keep pace, and we're developing products toward this end. A couple of examples would be silver sintering and topside cooled packaging. These are a couple of ways that we think we can solve these challenges in tandem with the suppliers of some of the passive neighboring components.
With SiC and GaN still being considered to be new materials, Kevin, will SiC and GaN eventually be mass produced to the same extent as silicon? And if so, when would that be the case?
Yeah, this is a good question, Mustafa. We're happy to report that answering the basic fundamental technical challenges related to high volume, high quality silicon carbide power device production, this is an exercise that's been completed, not just by Microchip, but by a handful of our esteemed competitors as well. So the answer to the question of will they be mass produced to the same extent as silicon is absolutely yes. The better question for me, I believe, is when. I wonder if what we're talking about here is really more about obstacles to adoption. So Microchip is indeed a semiconductor manufacturer, but more so we're a solutions provider. And while one person's opinion doesn't necessarily make it the biggest challenge, I personally feel that among the biggest challenges is the shortage of solutions. Remember, we're talking about two disruptive technologies in silicon carbide and gallium nitride. So if we want our customers to realize inevitable successes sooner, we as suppliers should be prepared to empower our customers with equally disruptive total system solutions.
I can also add that if we consider the total transistor market, we see that between 2020 and 2025, the compound growth will be 5.4%. When we talk about transistors, of course, I include silicon and the new material. If we go to silicon carbide in the same period, the compound growth will be more than 26%. If we go to GaN, the growth will be even higher, around 55%. So the growth rate of the new materials is very, very, very high. Not only that, but the main driving forces for the silicon carbide and also for the gallium nitride is electrification, because electrification is pushing the quantities up. And of course, as Kevin said, it's very difficult to say if there is a crossover between silicon and the new materials and when this happens, because it also depends on government and countries to put in place the right policies to increase the number of electric vehicles or to push electrification. But for sure, the trend is very positive. There are no reasons why the new materials cannot be produced at the same level as silicon in the next future.
A highly interesting look into the behind the scenes and the outlook for SiC and GaN. Well, our podcast is named Passion for Technology, and you've shown that both of you are passionate about wide-bandgap semiconductors. Now, I'd love to know more about the origins of your passion for technology. How about we start with you, Filippo, and Kevin, you just continue right after.
Thank you, Mustafa. I like this question. To be honest with you, when I was younger, I wanted to become a physicist. Theoretical physics is in my heart. My model is Enrico Fermi, who gave a big contribution in physics and, of course, in semiconductor physics. So I think most depend upon my preference for theoretical physics. I always say to my colleagues that when I retire, I want to spend most of my time studying quantum physics. So I think this is the origin of my passion for technology.
For me, this is also a great question to get some personality behind the people you're interviewing, Mustafa. So I appreciate this too. For me, even as an undergraduate electrical engineering student, I still didn't really know what I wanted to do with my career until I took on my first device characterization research project on silicon carbide Schottky diodes. And this is going back to the late 1990s. So when I finished my undergraduate degree, I then did an internship. I was very, very fortunate to do an internship at the NASA Glenn Research Center in Cleveland, Ohio, where I met sort of my version of Enrique Fermi, and he goes by the name of Phil Newdeck. Phil Newdeck was really a pioneer in some of the early silicon carbide epitaxial crystal growth studies. And indeed, they did some bulk crystal growth studies as well. When I looked at the polymorphism and the perfect triangular and hexagonal crystal facets under a microscope, I fell in love. This was fascinating to me. So the next few years was spent studying polymorphism, studying defects in the as-grown silicon carbide crystals, correlating those defects to device performance and reliability, which is now paying dividends for what we're doing today. So this was really the root of my passion, and I have been so lucky to have seen it from the days when we were taking little crystal ingots and making devices on them to now we're manufacturing high volume and 150 millimeter substrates. So it's really been a fun ride. I look forward to a blessed career going forward too in silicon carbide.
These are very, very beautiful, very personal insights into your origin stories. Thank you very much for those. Dear listeners, if you want to know more about SiC and GaN, visit ebv.com/GaN-SiC. That's ebv.com/GAN-SiC. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Filippo, Kevin, thank you very much for the insights that you've shared with us today.
Thanks for having us, Gustav.
Thank you.